entropy, free energy, complexity, time and error rate for construction. I've been very interested in evolution and lifespans, and what I have in another part of my video is that evolution trades off activity rate and lifespans. Activity rate has a positive, longer lifespans has a positive, but higher activity rate also implies that the organization is going to develop errors faster. Now, the description of entropy in the universe is that disorder is increasing. Now, this you can sort of think about it as disordered states have higher probability than ordered states. So with time, you're going to get more and more disorder. If you want to maintain order, you can maintain order in an organization like a human body by expending free energy. Of course, you can't get away from the fact that the entropy of the universe is going to keep increasing. So your maintaining the order of your body has to come at the expense of a disorder outside your body in the rest of the universe. Increasing disorder outside your body. Okay. So one very important idea is that we need free energy to maintain our human bodies, and we get that free energy by eating, and then you have carbs, you have proteins, fats, and then the body metabolizes that, it burns it, it breathes in oxygen, it uses that oxygen and it burns these carbs and all, and it produces stuff like little energy stores, like chemicals like ATP, ADP, etc., which go around the body, and they provide the energy needed for maintaining the organization of your body. So my interest in entropy, led me to ask some questions. Okay, what is a measure of order or disorder? And you're saying that okay, there is disorder is increasing. So how do we measure that increase? What amount of free energy is needed to produce a certain amount of order? So you want to move from disorder to order. How much free energy will you need to create order? And then there's also this issue that humans, we have an empirical observation that humans, amongst great apes or even other animals, take a pretty long time to get to maturity. It's about 17 plus years. And the question is why? Why is it that we take so long to get to maturity? Why don't we get to maturity faster? Because waiting to mature puts a cost on us, an evolutionary cost on us. We, after we get maturity, we can start acquiring resources. Before that, we have to be kind of taken care of and all that. So why does evolution not design our bodies to get us to maturity faster? Okay, so that's the question. Okay, so to answer these questions, I build a model, and it's just I was playing. I'm driving and I'm thinking of these things, and I think, oh, I would like to make a model. Or I'm lying in bed, I'm thinking, oh, how could I make a model to kind of get some insight into these issues. So do not take this model to be the finished work. This is sort of an insight. You can say it's a starting point. And this model is entropy, free energy, etc. And it's like on SSRN. You can take a look at it if you like. So in this, what I have in this model is essentially I'm saying that, okay, how much energy is needed to build a heterogeneous hemispherical structure. So you start out and you have all these little elements and you have to build a hemispherical structure. Order here is because you can arrange these little elements that you used to build it in a certain order, and then you have to put them in place, and the energy is expended in moving the elements from like say the center of the hemisphere to its proper position in the hemisphere. And I found these relationships. So you have these elements being put in the thing, so it takes a certain amount of time, and if you extend more energy, you can move it faster. That's the relationship between energy and time taken for construction. And also, if your sphere is bigger, and I measure complexity by the size of this hemispherical sphere, if it is bigger, then it will take more time to construct. Now remember, this hemispherical sphere is actually complex because this is allowing you, this process of construction is allowing you to put whatever element you want in which point. So it's a heterogeneous sphere. It is not just like you're just not making the same elements. Like, so these elements which are from the center of the sphere are can be different. Okay. They may be of the same shape, but they could be like one could be blue colored, one could be green colored, one could be red colored. So you have the choice, you have the freedom to choose how you're going to arrange these colors, and that's complexity. Uh-oh, I forgot to put a negative sign here. Time has to be proportional to the negative root of energy. So if you spend more energy, you can do the construction in less time. That negative is probably missing in the paper, which is there in SSRN. If you get the paper, you should just keep that in mind. So these are all intuitive, but it's like you have a formal model which looks into these relationships. So now, to come to that, back to that question about why does our brain take 17 years to mature? Of course, for some people it will take even longer, but here is the thing. So what I say next is, okay, if I speed up the process of construction, what happens to the error rate? And then I kind of say that, okay, if you're moving an element from the center to where it's its proper position in the hemispherical sphere, then if the element travels faster, it has a certain window of time to get into this proper position, and then there could be, there's a like normally distributed error, and if the speed becomes larger, then that window of time becomes smaller and smaller because the element will be moving very fast. So it has less time to get into, like it has needs to kind of have a smaller and smaller time as velocity of the element increases to stick to the right position. And that if it doesn't like make it in that window of time, then you get an error. So this error rate increases with velocity as the construction proceeds, and if the frequency of error is epsilon, then the formula for epsilon is this.